I feel bad giving you this formula because really it should make just intuitive sense, maybe from a geometric standpoint. So I'd like you to think about we've thought a lot now over here on the board and just now in our discussion about the probability of A and B occurring, but I'd like to turn our attention to the probability of A or B occurring. That is the union of the two sets, if you will. And I want you to think just now, draw a Venn diagram, and convince yourself why this should just make plain sense. So just take a second to think about it if you haven't before. I think maybe some of you have. And then we'll do this very simple example of this situation happening, right? Just to illustrate the points. So can you convince yourself using the diagram that holds? Just pick geometric areas. All that. Have you convinced yourself? Have you convinced yourself that it's true? That I don't know, I might call this like the inclusion-exclusion rule or something like that. Have you convinced yourself that it's true? If you were just to like add up the areas in this Venn diagram,
You'd overshoot.
yeah, you'd overshoot, you'd overcount the middle part, wouldn't you?
And you have
You add A and you add B, you've just counted the center part twice, haven't you? So you can kind of think about this as a correction for that, if you like.
You can also keep in mind that just having A and B can for
Maybe.
for having
Yeah, that could happen too, and maybe you could, pull it. It's all good. Okay. So let's do. It's not meant to be difficult. It's really just meant to illustrate this, right? So can you convince yourself that in this situation this makes sense too? What are each of these associated probabilities? Write it out. Do you get the thing you would probably expected to get, even if I didn't give you this rule? Hopefully it comes out to be the thing you'd expect it to be. What are we doing? A heart or a jack? Apparently that's supposed to be the probability of a heart plus the probability of a jack minus the probability of both, which sometimes can be just calculated by multiplying, but not here. But what are each of those probabilities, and when you add them up, do you get the right thing? Go ahead. Probability of a heart is 50. 13 out of 52. The jacks, how many of those are there? And how many cards that we could draw with one draw of a card? Is it possible even that you could get a card that's both? Yeah. Of course, it has a name. It's the Jack of Hearts. So what does that add to? 16 out of 52? And we can reduce that, what is that, 4/13? Brilliant. Okay, so I hope you see why even in a simple example it makes sense. Let me ask you maybe two follow-up questions that I think are interesting in light of this formula and in light of this situation where we have an or and some overlap. First of all, is it possible to have have the formula just be like the probability of A plus the probability of B? Does that ever work? Just to do that? And in what situation might that work? Where we can just sum the probabilities of A and B? Yeah. Yeah, or if you have a working engine, then you don't have a non-working engine, or something like that. I mean, whatever it might be, they're mutually exclusive things. Give an example in terms of cards. Yeah, if I asked what's the probability of drawing a heart or a spade, then suddenly this formula becomes simpler. We don't have to deal with this intersection Or do we? I guess we do. It's just the intersection is of size 0, right? So I want you to understand those situations, and the word that Sophia used, mutually exclusive, is a word you maybe even use in English, but that's a good word used in the situation in math class too. We're talking about probabilities. Those, so we call those events mutually exclusive. They just can't even happen at the same time. There is no intersection. Tell me also, because I think a lot of students mix these up, how does the idea of there being an intersection, how does that relate to the idea of independence? Because I think some people mix those up. They're like, these things can happen at the same time, so therefore they're not independent. What would you say to the person who says that? You can see why they might see someone might get those confused. They'd be like, well, they have an intersection. They're not independent. Independent would mean they're like far away from each other. They don't intersect.
The opposite. Your two things are mutually
If two things are mutually exclusive,
if you have two things that are mutually exclusive, then one cannot occur given the other. However, independence would mean that if one is true, then the other would occur in the same probability in the population of the other as it would in the entirety of a population. Therefore, if the two don't intersect at all, then there's no independence, as the probability of the one being instead of the other is 0.
wait, so what's the claim? Say it again.
Two things that are mutually exclusive are not independent, as if you have
Yeah.
a set of one things.
What's the probability, just to prove it using the rule, can you demonstrate that the probability of B is not equal to the probability of B given A in that situation?
Well, the probability of B given A would be equal to 0, so unless the
Correct.
probability of B is 0,
Correct.
then,
Good.
well.
Yeah, so in that sense, if they're mutually exclusive, then they're definitely not independent. That's true. What if they do overlap, though? Don't you hear the person who says, well, they overlap? They can't be independent.
Can be.
Yeah. Somebody.
Well, I don't know if that's clear. It's like it just means independence just means that the outcome of one doesn't affect the outcome of the other. So if you put a marble bag and you pick one, you put back and you pick another, those events, the probability of whether you pick a yellow the first time doesn't matter to picking a blue the second time. So you can pick both the yellow and blue.
Okay. Yeah, good. You want to add to that, Theo? Say your way. Okay. You want to unpack that a little bit?
It's like
Those big words. Thanks, guys.
It's like there were more lemons in the summer. People love ice cream in the summer because of the ice cream.
Okay, yeah, so those are things that can happen at the same time.
So they're
Things that are-
correlated, but it doesn't have a causation.
Okay.
But things that are independent are
The one thing I should say too, by the way, is that, and this is good humanities stuff here, isn't it? Too. When we, like, for example, we'll go back to like the male sport thing. Am I making some causation claim? I'm not at all. I'm just saying that they're not independent.
They're
That's all.
correlated.
I mean, I'm not making any causal claim. I'm just saying that. So is it true that summer and murders are dependent? The answer is like, yeah, they are, but not. We mean dependent in a way different than like the rest of all these. We mean that one probability is changed by knowing the other, right? But we're not saying that there's any causal relationship. So I want to make sure we're clear on that too. So I guess I'm not ready to talk about causality at all yet. Yeah. Anyone else want to enter the discussion too about the difference between things being mutually exclusive and being independent and that kind of idea? Nobody cares. Okay. Nobody wants to go any further. Maybe we've said it all. That's good. Let me give you one more like this, just to practice, and while I pass out your homework tonight, which is on this sheet, and you'll spend the rest of the class studiously working on it today. Some of these are challenging, so I think I want to give you some time to work together with your neighbors on this. And you can like let all this sink in now too. This is hard. This is hard stuff to think through. Know that in this survey, if you donated food, you're among those people who said the 65 people who donated food on that list. Do you see that? Makes sense? So what does that mean? Does that include people who also donated money? If that includes all the people who donated food, then the answer, I guess, is yes, right? Understand how to interpret these numbers? So answer that question. Did you already answer it? If you donated food, then you are for sure counted among these 65 people, right? Regardless of what else you may have done or may not have done. Huh? Yeah. Okay, so now to what extent is that true? Yes, it is. Oh, murder, sorry. Oh, because it's summer, it's the underline. Yeah. Murder and you sure it's murder?
14.5.
Ice cream and like drowning. Because it's both are caused by the
Ice cream drowning
not,
and
murder.
murder.
No, but yeah, you can swim.
Yeah, but very few.
But if you don't know the winter, you're probably like an actual swimmer.
True. Yeah, that is a classic example though. I just, ice cream and drowning is the classic. Probably murder too, yeah. Nobody wants to go out in the winter, it's too cold to murder.
Actually, those two studies show that sunlight tends to give a person more energy, but also makes them more irritable. Also, whenever you talk about hurricanes, it makes me able to do this in my notebook.
Can we talk about, yeah, okay, that's good. Did you answer the question?
Oh yeah, it's done. 32.5%. That was done a while ago, so I figured I'd draw it.
Cheyenne,
Well, it's alright.
come do this then when you're ready.